Welcome to the lecture, guys. In this lecture we are going to continue our Irodov solution series, and the chapter we are taking is gravitation. So these questions may come in your IIT JEE Advanced or IIT JEE Mains. Okay, so I haven't solved every question from this chapter, but all those questions which may come in your IIT JEE Advanced or IIT JEE Mains or in KVPY or in your NEET. My name is Anmol Kumar. I am MTech in Aerospace Engineering from Indian Institute of Science, Bangalore, and your instructor at itpathshala.com. You can contact me on these number. You can give free examination on my site. Before going into the lecture, guys, please like, share and subscribe my channel. Don't forget to share the video and please hit the bell notification icon. Our aim is to have 100 like on this video because these questions may come in your JEE Advanced or JEE Mains examination or in KVPY. So please give it a thumbs up before even going into the video itself. It's my request. Please check out my other cool videos on part 1 of this series, then part 2 of this series, kinematics, motion in a straight line, concept with numericals, HC Verma solutions, tricks to solve your question in JEE Advanced or JEE Mains or even in NEET within 1 minute. So we are starting our lecture with this particular problem. This is a cavity problem. Okay, frequently being asked in the examination itself and can be asked. Until now it is not being asked, but can be asked in your JEE Advanced or JEE Mains. So in this problem what you are having is, you are having a sphere with a center C1, let us say, and then you are having a cavity with a center C2, and you are intended, you want to find the electric field at this particular point P inside that of cavity itself. Okay, the distance in between both of the center is given as L. C1, C2, there is a distance in between them. Let us say it is L as per the question itself. The density is given as rho, and let us say this is our point P. Now what I am going to do, because I know that gravitational field is nothing but a vector quantity, so I will be needing the vectors itself. Which vectors? Position vector. So henceforth I can say that this is my first position vector with respect to C1. This is my position vector number 2 with respect to C2 of this point P, and this is my third position vector, let us say L vector, with respect to C1 itself. Now guys, it's very good if you know the formula directly. If you don't know the formula of directly of this gravitational field inside that of a sphere, let me tell you by the small trick or the small concept itself. Okay, so now let us say this is your sphere. Okay, it's having a uniform density rho. Again, let us say you want to have the field inside this sphere at a distance r. Okay, so you can apply the following Gauss concept, which says G dot ds is nothing but must be equal to minus 4 pi into G and mass inside that of contour which we are considering over here. This is the contour, this is the dotted contour which I am considering over here. Okay, so G will be coming out to be G into 4 pi r square, this is the cut surface area of this contour over here, equal to minus 4 pi G m inside will be density multiplied by the adequate volume of the contour itself, which is nothing but this over here. So you'll be having G as minus 4 pi by 3 G rho r. Now guys, to solve a cavity problem, you should be remembering that this is the formula you are getting. It's fine. Okay, you were having a positive density over here. Okay, now in the cavity problem, because you are not having any mass in this cavity, you are devoid of the mass. I'm doing is I'm dividing my cavity into two masses system over here. Which first is the plus density system and second is the negative density system, the basic drill. Okay, so that's the trick how to solve the cavity problem, even in the electrostats also, even in the center of mass system also, or even in the any kind of cavity system also. Okay, so what I'm considering over here, that I am having two spheres. Okay, one sphere of density positive sigma, second sphere of density negative rho over here, positive rho and a negative rho over here. Okay, so I know that because it's a vector quantity and I want to find out the gravitational field at this point P, I can use the superposition principle, which says the G net should be equal to G1 plus G2 itself. Okay, now you are having this following guy over here. Okay, this is a vector, this is a vector. You are having the positions vector also over here. Now what you can do is, you can just put all the values over here. So for the first one, for the positive rho sphere case, okay, 4 by 3 pi G positive rho r1 vector plus, because I'm running out of the space over here, I'm writing it over here, 4 by 3, you shouldn't be forgetting about this negative over here, pi G minus rho into R2 vector over here. Okay guys, this way, this is the result you will be getting after applying the superposition principle itself. Okay, I'm erasing this because I am not needing this. Okay, and what I'm writing, what I'm taking common as minus 4 by 3 pi G rho, and I'm left with plus R1 vector minus R2 vector over here. Now from the vectors itself, if you see this vector triangle over here, you will be knowing that R1 vector is nothing but L vector plus R2 vector. So L vector is coming out to be R1 vector minus R2 vector itself, guys. Okay, so you are left with minus 4 by 3 pi G rho L vector, which is the appropriate solution of the following problem, guys. Okay, so nothing fancy about that. Okay, what you have done is two things. First, you have divided this whole cavity into two parts, plus rho minus rho. Then you have taken the vectors. If you don't know the formula, derive it live. Okay, as I've done it over here using the Gauss trick itself. Then use the superposition principle, apply it, use the vector formula itself, vector concept itself, and you'll be having your easy money over here. Okay, so guys, let us take this particular problem over here. Now why I've taken this particular problem over here is because most of you guys are having problem in the work done and the potential energy concept itself. No, so let me tell you that work done by a conservative force is negative of change in potential energy, and work done by any external agent is nothing but it will be equal to the change in positive change in the potential energy itself. Okay, that you have to keep in mind. We'll discuss this concept in the work energy concept itself when I will be releasing the video, or you can take the online classes which I deliver, and I will cover all your doubts over there only. Okay, so now you are given with a particular solid hemisphere over here. This is your solid hemisphere. You are having a mass at the center. Let us say this is my test mass at the center itself. Now you want to evaluate the work done by this particular solid hemisphere to move this particular mass m naught from the center to the infinity itself. Okay, that's your problem. Okay, so what I will be doing is I will be using this concept, but now in a very innovative way. Okay, so what I'm doing over here is let me have the smallest chunk for this biggest mass over here by using the first principle itself. Okay, what I'm taking over here is I'm taking a smallest chunk as my spherical shell. This is my spherical shell, which is having a radius r, small radius r from the center itself. Okay guys, now I know that the mass of this shell will be equal to mass of the hollow sphere, because it's solid, upon the volume of this hollow hemisphere into the volume of the following shell, 2 pi r square, and let us have the thickness as dr itself of this particular mass system, particular shell. Okay, nothing fancy about that. If you have done mechanics good enough, then you will be knowing what I am doing over here. Okay, that will be a piece of cake for you. Now mass of shell is coming out to be mass of solid hemisphere, sorry, mass of solid hemisphere, and after removing all the variable, 3 r cube into r square dr. Okay, now you are concerned with the potential itself, so I'm writing the potential here, minus g, mass of the shell itself, 3 mass of the hemisphere upon r cube r square dr, and you are r distance away from the center. Okay, so you are left with the following formula: g 3 mh r cube r dr. Now let me remind you that you are going from the center, which is at 0, to capital R itself. You are integrating the particular formula over here, and you are left with minus 3 by 2 g mass of the hemisphere itself upon r. Okay, so you're left with the particular following formula. Now this is the potential. You want to find the potential energy, just multiply it by the test mass itself. You know that potential energy is nothing but test mass multiplied by your potential itself. So I am having m naught minus 3 by 2 g mh upon r. Okay, that's my potential. Now this is the potential for this particular solid hemisphere. Okay, complete potential for this particular solid hemisphere at the center itself. You know that at infinity potential is 0. Your v is 0 at infinity. So potential energy at infinity will be equal to 0 itself, and potential energy at this particular center is nothing but it is equal to something like this. Okay, this is minus 3 by 2 gmh upon r. Now you want to find the work done. I know that work done is nothing but minus of delta u, so I'm writing it as minus u2 minus u1. Okay, so u2 is nothing but it is equal to 0, so minus minus plus giving you answer plus u1, and you know that u1 is nothing but we have find the value of u1 as follow over here. Okay guys, so that was the solution. Now if you want to find the work done by the external force, because they can ask you the work done by the external force, you can use the particular formula over here. The answer will be plus 3 by 2 gmh upon r. Okay, in this it is minus 3 by 2 gm upon r. Okay, that's the solution of the following video guys. Okay, I'll bring more solution and to more important question, okay, for the Irodov itself. So we'll meet you in the next lecture. Until then, goodbye guys, and don't forget to check out my other videos, and please like, share and subscribe my channel if you loved my channel itself. Okay, thank you guys.